This is a 3D printed two-stage planetary gearbox, and I'm going to try and get as much torque as possible out of it. I'm aiming for about 150 Newton meters. That's like 110 foot-pounds of torque. It's like having a 1 meter lever arm attached with 15 kilos of weight on the end. It's way too much to ask of a 3D printed gearbox, but it's going to be fun trying out various different materials and testing them to the point of destruction. That doesn't sound good. 130. Whoa! No way. Before I start destroying this actuator, we should probably take a look at the design and discuss why I'm building it in the first place. If you recognise this design, it's because it's based on Gabriel Levine's open torque actuator, and I'll leave a link to that in the description below. I've made some significant changes to the original open torque actuator design, but the biggest change is adding a second stage to the gearbox to further reduce speed and increase torque. It's driven by this brushless motor on the back, which is an Eagle Power 8318 100 kV motor, and that's driven by an O-Drive S1 controller. And that goes into the back of the first planetary stage, which sits here, and that is an 8-to-1 reduction. Then there's a second stage of planetary gears that sit here. That's another 8-to-1 reduction. So in total, I have a 64-to-1 reduction within this gearbox. Effectively, we have two stages of this planetary gearbox assembly like this. So in the middle, we have the sun gear. And then around the sun gear, we have the 3 planetary gears. And then around that, we have the outer cage gear, or the holder that's holding it all together. So if I turn the sun gear in the middle, you see the planets start to revolve around the sun. What's great about it is you can get an awful lot of torque out of a very compact design, and that's because rather than just having one gear meshing with another gear for a reduction, you have 3 gears in mesh with another gear, so you have much more teeth in mesh, so you can put more torque into the gears. So how do we get to our reduction of 8? Well, our central sun gear has 9 teeth, our planetary gears have 27 teeth, and our outer gear has 72 teeth. So if we divide our 27 tooth planetary gear by 9, our sun gear, we get a reduction of 3. And then our outer gear by our planetary gear, which is 72 over 27, that's a reduction of 2.6 recurring. Multiply 2.6 recurring by 3, and we get our reduction of 8. So with a 64-to-1 reduction gearbox and a motor that can supply about 4 Newton meters of input torque, we should theoretically get 256 Newton meters of output torque. But of course we won't, because we've got frictional losses inside of the gearbox. It's not 100% efficient. If you're wondering why I'm trying to get so much torque out of a 3D printed gearbox, well, it came about from an idea to build a mini Mantis just big enough for me to sit on. The Mantis is a 2-ton hexapod robot that I built about 12 years ago. It's very heavy and cumbersome to move around. I was talking to James Bruton one day and I said, wouldn't it be fun to make a smaller electric version that I could just sit on and take to shows, and it's small enough to put in the back of a car, for example. Well, I worked out for some rough calculations that I would need about 300 Newton meters of torque on each leg joint. So actually 150 Newton meters of torque from one of these gearboxes still needs to be doubled up, so I need another 2-to-1 reduction, and the idea was to put a belt drive reduction on the output stage of the gearbox and to give me my 300 Newton meters of torque per joint. As you can see from my original CAD models, I was planning on using these low-cost linear actuators. They can generate enormous amounts of force, however, they're very slow and they're not terribly well made. So it's all very theoretical right now. I really don't know whether this gearbox is going to take the strain of the kind of forces I'm going to put through it, but I think the best option for the joints on the legs is to be driven by a high-powered brushless motor like this one, and through either a planetary gearbox or something else. Maybe it'll end up being a planetary stage 1 and a cycloidal stage 2. I don't know, but I'm going to test this to death anyway and see what happens. So let's take a look at some of the materials I'm going to be using. I've got a resin print here. This is an ABS-like material, but I don't suppose it's very strong, certainly not as strong as ABS. I've got Polymakers PLA CF, prints really beautifully, although the carbon filled might be a little bit too abrasive for the gears. I've got Polymakers PC Max here, so polycarbonate. This one I expect to do pretty well. High hopes for that. And I've got PA12 CF here, so this is a nylon with a carbon filled. Now this should be pretty good. Again, printed on Bamboo Labs X1 carbon printer. Looks really nice. but the carbon might be a bit abrasive. Next to that, I have this I printed on again on the bamboo, and this is a IGUS material. So IGUS, known for doing gears and bushings, that one should do pretty well. Then I've got some sintered parts here, some SLS nylon, so this should be the best of all of them because it's been sintered and it's a solid piece. And next to that I've also got some sintered nylon, but this has had glass bead nylon, so it's GB, glass bead nylon. So that should be pretty good too. Okay, I think it's time to dismantle this gearbox and take a look at the internals. First of all, I'm going to slide the motor out of the back of the gearbox assembly. The screws have already been removed, so that just comes straight out. The next job is to remove the faceplate adapter. This adapter is designed to take a piece of aluminium 2040 extrusion, and that will form my load arm when I'm doing my load testing. There are 3 screws that hold the faceplate onto the second stage output, so I'm going to take those off first. Now those are removed, you could take the faceplate off, but it's easier to take it out if I take out the second stage bearing holder. So I'll take these screws out and then the whole thing will come off together, including the faceplate. Now we can remove the first of the outer gears to reveal the Planet gears underneath. The Planet gears are held together in this cage and they come off in one piece. As you can see, the second stage sun gear is connected to the output of the first Planetary gearbox. I can now remove this next segment, which contains a large bearing for the second stage Planetary gearbox we just removed. There it is, another 90mm OD bearing, 70mm ID, and there's 3 of these in the gearbox and they take the majority of the radial and axial loads. I can now remove the stage 1 outer gear and that will reveal the remainder of the gearbox. We can see our stage 1 Planetary gear assembly. So without those outer gears in place and the bearing holders, you can see how you could just keep stacking stages on top of each other. This method can give you some very large reductions in a very compact space. In order to test these gears, we need some kind of a device that will slowly ramp up the input torque on the motor and measure the output torque of the gearbox. Behold, the Denton Newton meter-o-matic. Yeah, I'm quite proud of that. It even comes with a white coloured dial option. Let's take a closer look. So I've bolted the motor down to a couple of pieces of 2040 extrusion, and I've added this 2040 extrusion lever arm on the front. This is approximately 300mm long, and it touches down on this force sensor here. The force sensor is connected into this can bed RP2040. It's quite a low cost module which comes with a can built in, which is quite useful. I'm also using the I2C to run the force sensor and a serial port to run my Dynamixel, which runs my Newton meter needle here. I've got power coming into my O-Drive S1 controller on the back of the motor, and that's connected via the CAN bus to my RP2040 module. The power loops through to the same module, which will take up to 24 volts, and also loops down to this DC-DC converter to give 12 volts for my Dynamixel. Here's the view from the back. You see the O-Drive S1 controller with the CAN bus connected and power, and the RP2040 and regulator. I'll be connecting the USB port up to my laptop, and that's how I'll control the whole device and get all the data I need from it. You may be wondering what's going on with this quirky looking dial here. It goes from 0 round to F. Well, that's because my CAD package didn't like doing 10, 11, 12 and so on. It spread the digits out really badly, and I needed 15 of them because I wanted to get to 150 Newton meters. So I've gone hexadecimal. 0 through to F, so we get to 9. For those who don't know hexadecimal, we go 10, 11, 12 and so on, but we use letters to represent those numbers. So that's why it says down here, Newton meters times 0xa, because that's also in hexadecimal, so multiply by 10. So this is 10 Newton meters, 20 Newton meters, 30 Newton meters, 100 Newton meters, 110 Newton meters, etc. Yes, it's a bit quirky, but I like it. It's not even needed because I have digital data coming out of the Arduino here, but it's a nice visual representation of what's going on. I've got my laptop hooked up ready to receive the data, and I've got a power supply here which is 24 volts at 12 amps. There's a simple formula that tells me at 12 amps the maximum torque the motor can supply is approximately 1 Newton meter. So once I get above 1 Newton meters of input torque, I'll have to get a bigger power supply or a battery. There are various data streams coming out of the Arduino into the laptop, and I'm going to be using a piece of software just to graph that data so I can look at it as the torque ramp builds up. I'm going to start by sending the command to enable the motor. C for calibration. Look at that. My dial does a little calibration thing. It calibrates the sensor. In fact, if I move this arm out of the way a minute, I should be able to push down on this, the force sensor. There we go. The harder plate, here we go, try this. The most force I can put into that sensor is 60 Newton meters of pressure pushing down on it. And so when that motor rotates, it's going to do the same thing. It's going to push down on that sensor and it's going to drive that needle up and also give me lots of data here. Okay, that's reset. I'm ready now to fire the motor up and push down on the sensor. I've got it set right now to only supply up to half a Newton meter of torque, but I can increase that in a minute. But let's try half a Newton meter first. Here we go. All right, there it is, it's building up. Okay, let's pause that there. So, first thing I noticed is that the needle went up in stages, like that, rather than smoothly. There was a smooth torque ramp, but the needle moved kind of in stages. That is probably the stiction in the gearbox as it gets stuck and then moves a bit further. So that'll probably be the friction inside of the gearbox that's causing that sort of staged move. We reached 26 Newton meters. Yep, that looks about right, same as my gauge. The efficiency was running at 80%, which is pretty good. I think like Planetary Gearboxes, if they're running at 80% plus efficiency, I think that's reasonably good. The way that's calculated is that we got to a half a Newton meter of input torque. So theoretically, with a 64-to-1 reduction, we should be able to get 32 Newton meters of output torque, but we didn't. We only got to 26. So dividing 26 by 32 and then multiplying by 100 gives us 80% efficiency. I've increased the input torque to a maximum of 1 Newton meter. I've replaced the power supply with a LiPo battery. Let's try this again. Ooh, I just heard something cracking. Let's stop it. Well, I was definitely pushing more force in. 54 Newton meters. That's pretty good. And there was definitely some not very good noises coming from that gearbox. Let's have a look at the data. So torque going in, we did indeed get to 99 or 1 Newton meter. Yep, 12 amps. Measured output torque, 50 Newton meters according to this. So the gauge basically goes up and records the peak and never drops down, but once this had settled, it was sitting at about 50 Newton meters. Yeah, again, efficiency sitting up at about 70, high 70s, low 80s. The dubious cracking noise that I heard, I think it's the fixings that are holding the motor gearbox down. Remember, this is only PLACF, but I'm pretty sure it's those that are cracking. I've added another fixing in, and as I tightened up the screw, the mount actually cracked a bit. So it could have been that we were hearing, or it's possibly the gearbox, who knows. Let's give it a go anyway. Here we go. It's 1 Newton meter. Whoa! That's impressive. Okay. Wow. I forgot to screw. So I was correct in my assumption that it was in fact the mounts that were breaking and not the gears, which is a good thing because I can probably improve that. And I did indeed add some additional mounts on, but I forgot to screw them down to the board, so they did no help whatsoever. But it's basically
torn, yeah, the PLA mounts clean off, which is not that surprising. You can see here, look, 70 Newton meters. It's pretty impressive before it tore the mounts off, so it probably would have gone further. I've replaced the first of the brackets. This one is printed in the PA12CF, and I can already see there's way more perimeters than the PLA CF. So let's go in. Way! There it goes. Crikey. 80 Newton meters. The bit that snapped this time, oh my God, it's torn the fixings clean out the front plate. I thought it had pulled these M4 captive nuts through the front plate, but it hadn't. It looks like the bolts that were being used to attach the front mount on were never actually deep enough in to pick up on the M4 nuts. So I don't really know how that was staying in place. You can see the kind of forces involved, how it's wrinkled up the plastic there. I shall get some longer bolts, and I've also got a PA12CF version. Let's try it again. Torque building. Can we get past where we were before? Oh, look at that. It was nearly at the top. Yes! 100 Newton meters out of output torque. That's good. 100 Newton meters. I mean, I'm impressed. At 100 Newton meters, this front plate is really struggling with those 3 fixings. So I'm going to try and put 3 more fixings in here. And look, that screw even got bent completely out of shape. Here's my new part, printed in polycarbonate with 3 additional fixings. So let's try it again once more with 2 Newton meters of input torque and see if the whole thing survives. Building up. We're just about to hit 2 Newton meters. There. Well, something went bang. Let's have a look. Yeah, okay. Now that feels like it's definitely that gear that's gone, probably the sun gear, because that's completely loose now. But it did get, look at that. Hang on a minute, it's gone further. It's 100 and, what is that, 110 Newton meters? According to the data, the sun gear took 13 Newton meters, 13.25 Newton meters before it snapped. Assuming it is the sun gear, I'm pretty confident it is. Let's take it apart and have a look. Oh yeah, there we go. There indeed is what's left of the sun gear. Looking at the way that this sun gear has sheared, it's nearly gone directly through that weakest point on that layer line there, although there is some material from another layer still stuck to that base plate. Given that the gear has sheared exactly on a layer line, the most important feature might be the layer bonding of the gear rather than the material strength, in which case PLA may do very well because it's very good layer bonding. The next tooth I've got in place is actually polycarbonate, so it's a much tougher material, but is the layer bonding as good? Let's find out. 1 Newton meter. 70. Sheared clean through the layer line as expected. Maybe again it could have got a bit more strength if it had been printed solid in the middle. $110 Newton meters. PLA for the win. There you can see just how good the layer bonding was on that polysonic PLA, because it's actually sheared very roughly through multiple layers. A material that I use rarely is PETG, but I thought I'd better give it a go for all the PETG fans out there. 1 Newton input. Ooh, there she goes. Saying about 82 here. Yep, it's a fairly clean break, but did surprisingly well. Next up, I'm going to go with this resin printed gear. Ooh, that sounds crunchy. 75, just over 75. Look at the state of that. Here's what's left of the resin gear. Next up is PA12CF nylon. 45. Nylon is super strong, but I guess the layer bonding, it's all coming down to this layer bonding. It's gone straight through the layer line, the bonding has failed. So next up I'm going to try my IGUS material. This is I150PF. Doing good. Oh, there you go. 99 Newton meters. I mean, it's still not as good as the PLA, but it's one of the best so far out of all of the FDM prints. This one's just come off the Bamboo X1 carbon, and this is printed in ABS. It's 1 Newton meter input. Whee, there we go. 75 Newton meter output. Well, it hasn't gone completely at the base layer. It's actually snapped off where it started a little bit of infill. So maybe I could have got a bit more strength out of it if I'd have printed it completely solid. Next up is polycarbonate ABS mix. 1 Newton meter. Yeah, just over 75. Split through the layer, bonding just where we'd expect it. According to the polymaker literature, in order to get the full mechanical and thermal properties of PC ABS, the part should be annealed in an oven at 100 degrees for 2 hours. So this is a laser sintered nylon. This should do quite well. Here we go. Come on, sintered nylon. But 100 Newton meters. Well, that's what I kind of expected. I mean, it is a solid sintered nylon part. I've increased the input torque to 3 Newton meters maximum, which means we might be pushing nearer that 150 Newton meters output torque. Going up. 25 amps. We've definitely gone past it. Oh, yes! Come on! 150 Newton meters out of 3D printed gearbox. Definitely signs of things starting to crack and make noises, but that is impressive. There's 2. There's 3. Oh! It wasn't a fluke, but it obviously is right on the edge of what was capable. There's a sintered nylon sun gear sheared clean off through one of the build lines. Next up, I'm going to try this multi-jet fusion part, which again is solid nylon but printed on a MJF printer. 1 Newton meter. Oh, according to this, we peaked at 115 Newton meters output. Ooh, I think that seized the gearbox up. It's sort of torn through it, left this little mountain, and it's really smashed up the gear inside of there. It really has shattered a bit like the resin print did. This next one is multi-jet fusion but glass bead filled. 1 Newton meter input, 2 Newton meters input, and it's gone. 90 Newton meter output. Maybe I got my glass beads mixed up. Not such a clean shear on this multi-jet fusion nylon. Just a little bit lumpy bumpy, but it hasn't broken up like the last one. I could of course print this entire gear in metal, which I may well do, but I've also got this idea, which is having a spline down the centre, so you can 3D print your gears still and then have a smaller metal spline. The spline probably isn't large enough, and it's probably just going to grind out that centre core on the plastic, but let's give it a go. There's 1 Newton meter input. Oh, still going. That was really impressive. Hang on, did we get to... Yes! Look at that! I can't believe that worked. I mean, there was definitely starting to break down towards the end there, but that spline, a printed gear on a spline, I really didn't think that was going to work. I'm going to run the test again and see what happens. 70 newtons, 100, 120, 140. Oh, there we go. 140 Newton meters. That's pretty good. I'm really interested to see what has gone snap in here. No way. What? You're gonna be kidding me. It snapped the titanium. I really thought it was gonna strip the gears out first. That has snapped off inside of there. It's twisted at the core before it snapped. That's incredible. Polycarbonate plastic outer is actually in pretty good shape. I do have this metal 3D printed sun gear, so now we can truly test the capabilities of the gearbox and see what breaks if I put the full 4 Newton meters of torque into the input side. I've increased my scale because I have to rescale it because it only goes to 150 Newton meters, and this is going to push past that, possibly up to 200 Newton meters. So now 75 should be about 150 and A should be 200. So let's try it first at the 3 Newton meters input torque and see how it fares, and then we'll see what happens when I push it past that, what part of the gearbox is going to give out next. Sounds interesting. About 135 Newton meters output torque. Starting to make some interesting noises. I've increased the input torque to a maximum of 4 Newton meters, which means that we could be generating about 200 Newton meters of output torque given the 80%-ish efficiency. So we should be getting to the A marker if we get there without something else detonating. 100, 120, 130. Whoa! Wow. Well, the gears never stopped. Yeah, so the arm mount has sheared clean off. Interesting. Reviewing the footage, you can see it's the support that's the first thing to go. 130. Followed shortly by the arm. You can see it starting to split here just before it explodes. Whoa! The front mount is now polycarbonate. The front arm is actually PLA because I think that's that layer line issue, so it's probably got better bonding for that particular part. Polycarbonate because it's tougher to screw down through. I've had a moment of realization. The force cell that I'm using has a 100 pound limit of force, and it's about a foot long lever, which is 100 foot-pounds of torque, which is equivalent to 135 Newton meters. So I've reached its capacity. To increase the capacity of the Denton Newton meter-o-matic, I need to bring my load cell this way and increase the lever arm length. If I bring the arm length out to around 500 millimeters, that should give me over 200 Newton meters of capacity. Given that my gearbox is about 80% efficient and there's a limit on the motor of about 4 Newton meters of input torque, that should be more than enough. Allow me to present the Denton Newton meter-o-matic 200, because it can go to 200 odd Newton meters. It's not quite as elegant as the original design, but all we need to do is see how far this gearbox goes. The lever arm is ridiculously long. It goes out of shot there. It's actually a 1 meter long lever. It's 500 mil from here to the force point. I've left it that long because I need a piece that long later on, and it's the only bit I've got. Remember, the scale is doubled, so we want to see it go around to the A mark, which would be about 200 Newton meters. 120. Yeah, 170. So I've peaked out at 170 Newton meters, which is still pretty good. I was only ever aiming for 125 to 150, so that's more than enough. I've switched out all of the PLA carbon-filled gears because I think the carbon-filled element is going to cause more friction in the gearbox. So I've replaced it all with the IGUS gears that I printed earlier. That's why there's a white stage here now. However, when I took it apart, I noticed that there was some pretty severe damage on the output stage. On the initial design, the final output stage was held on to the second stage gearbox using 6 M3 stainless steel bolts. And you can see just how bent that bolt has become. So I've replaced the bolts with these red aluminium spacers. The spacers come through the second stage gearbox, through the bearings and through the gear, and they will pick up on the new faceplate like this. So they'll be pushing the faceplate round, and there's also 3 high tensile bolts that bolt down through. So now we have a much larger axle coming through to the faceplate with high tensile bolts. That should make that a lot stronger. So here we go, lower friction hopefully. Let's see how we get on. Making some horrible sounds. Oh, about the same, just over 170. Let's have a look on the data. We got to 173 Newton meters of output torque. Efficiency was dropping off to about 65% by the end, so maybe it wasn't friction, maybe I'm just reaching the limits of what I can do with a 3D printed gearbox at the moment. Time to move on.
Let's take a look at the leaderboard. In the left-hand column, the FDM prints, with PLA coming out on top, probably due to its superior layer bonding. PC ABS probably would have done better had I ever annealed the material in an oven. In the middle column we have the nylon and resin prints, SLS performing better than MJF, and of course resin at the bottom, but still doing pretty well. And as we would expect, the metal performing the best in the last column, the titanium gear doing 170 Newton meters. But the real surprise was the metal splined core with a polycarbonate outer did surprisingly well.
I've just had a shipment of 3D printed parts from PCBWay, which is my sponsor for this video. Let's take a look at what's in this box. Yoink! Well, as you may already know, PCBWay don't just make circuit boards and PCB assembly, they also do engineering like CNC machining, sheet metal work and 3D printing. And what we have here is more or less an entire gearbox 3D printed in nylon. The reason I did that was I didn't know how far I could push FDM prints. As it turns out, they've done pretty well, apart from the one gear that keeps breaking, which I also had PCBWay print me in aluminium. So this is a beautiful looking set here. This is all nylon, this is non-coloured, so I had the rest of it dyed black, but this one obviously has been left as a standard white nylon gear. The even more exciting bit is what I've got over here, because you know I'm a fan of their UTR 800 transparent prints. Well, what if we had a transparent gearbox? Now the reason behind this was I was thinking there's some issues in the gearbox, such as backlash, because we want to try and reduce the backlash as much as possible. So I thought if I printed enough of the gearbox in transparent, could we see what's going on inside the gearbox? I don't know, but I think it's going to look really cool. And I've done some RGB coloured gears to go inside, and I'll put one on each segment so we can see what's happening inside the gearbox as it's working with these beautiful PCBWay UTR 800 prints. So looking forward to assemble that just to see how cool it looks. I'm often asked how much these parts cost to print, so let's take a look. One of the more expensive parts would be this small aluminium sun gear. This is about $29 to print. And then the equivalent nylon part would be $4.50. A larger nylon part, such as the outer gear here, you're looking at about $24. And the equivalent in the UTR 800 is about $37. One of the smaller white non-dyed gears, this is about $7. I can't quite see as much as I wanted to because of course there's bearings inside of these two parts here, so it looks like they're really reflective, but it's the outside casing of the bearing that we're seeing through those clear parts. I don't have another motor at the moment, but I just made this adapter for my drill so we can see it moving. Funky. I don't think it would actually last under load because I'm not sure how strong this material is. Although on the outer gears, maybe it'll be okay. I was pretty careful when I was self-tapping the screws in because I was worried I was going to crack something. But it went together nicely and I think it looks really cool. If you need any of PCBWay's services, don't forget to go and check out their website at pcbway.com. I'll leave a link in the description below. I've got my 1 meter lever arm attached to the gearbox now. It's still got that metal second stage sun gear, and the rest of the gears in there are FDM printed plastic in the IGUS material. So now what we can do is slowly start adding some proper weight on and seeing how the gearbox behaves lifting proper weights. I've recoded the Arduino, so now it's going to lift from about here, go up to 90 degrees and come back down again. If anything does go wrong, I've got a chair down here with my PCB cushion on it, so hopefully that's going to absorb any shock loads if this comes crashing back down. That backlash probably looks quite severe, but in a real case scenario where I was using this in the leg of a hexapod, I'd actually put another position sensor on the output shaft of the gearbox, and the backlash would be compensated by closing the loop on the output shaft. So I'm just going to power this up here. It's going to start on a very short cycle. Of course, most of the torque is when this lever arm is at 90 degrees, so it's going to start at its hardest position and move up to less torque. On my meter over here, I've actually got the amount of power being supplied, so if I just put some force on this arm, it went up to about 500 watts of power. I can speed this up and of course increase the range. Now I don't need to test the weight on this lever arm at this speed, because when a hexapod takes a step, the only time it needs speed is during the step phase and not during the support phase when it needs power. So it's good to know the motor has plenty of speed to be able to take a step fast, but it only needs it to support lots of power or produce lots of power and torque when it's in the support phase. I'm definitely not going to put a weight on it when it's doing that speed. So I'm ready to put my weight on now. I'm going to start with this 2.5 kilo weight, which at a meter should be 24.5 Newton meters. I'll lower it down onto the cushion, power up, and let's start the range of movement. It does build up slowly so as not to suddenly jump to a position. Seems to be handling that pretty well. Let's just increase the speed a little bit. And you should see the power increase. Still handling that pretty well. Go a little bit faster. And it's not really going above 220 watts by the looks of it. So I don't really want to go much faster than that. But I'm going to. That's not bad at all. All right, let's bring it to a stop. I've put two 2.5 kilo weights on here now, so we're up to 49 Newton meters. That's a hell of a lump on there. It's a bit sketchy, to be honest, throwing this around, because if something does give out, there's quite a lot of weight to drop. And I think I'm not going to go as high because I noticed it was going over centre slightly, and I don't want it to go that way and then swing all the way back round and possibly go through the back wall of my workshop. What are we looking like on the power? Okay, 300 watts to bring it up. Let's go up on speed a little bit. I'm still handling it pretty well. That's pretty good. I know I said I wasn't going to speed it up, but it's handling it so well, I kind of feel like I have to. Looks like it's peaking at about 400 watts. That's pretty impressive. More weight. I've got 7.5 kilos on here now. Like, that's a lot of torque. If I just pick up this 5 kilo weight and lift my shoulder, that's quite a lot of effort. I know I'm not particularly hench, but I don't know whether I should embarrass myself trying this. No, I'm not going to do that. I'm just going to hurt myself. I'm sure some weight trainer out there will be like, that's pathetic, but that's a lot of weight. Definitely seems to be struggling a bit. We're up at 500 watts just holding that position. Right, let's increase the speed. There we go, just over 500, 550 watts. It's a lot of creaking coming from the board, but I think that's fairly good. I know we've measured this at much higher torques, but when you actually see a physical weight, on the end of a lever. And you can feel how much force that is. It's a lot of torque coming out of that, but we can go higher. We've got 10 kilograms on the end now, which is 98 Newton meters, or 72 foot-pounds of torque. Oh, that's really struggling. We're getting up to 650 watts, but it's still coping. Let's go up on the speed. There's some significant creaking noises coming from that gearbox. Let's go up again. Peaking at nearly 800 watts, but it's still coping. It's 100 Newton meters. Nice. Obviously, I'm not going to stop there. We're now at 12.5 kilos, 122 Newton meters, or 90 foot-pounds of torque. God, it's barely lifting it off the pillow. I don't think it's made it into shot. Oh, there was definitely a cracking sound then. What are we getting up to on the power meter? 900 watts. Right, a little bit faster. Was that about 1,000 watts? Go one faster. Whoa! What happened? I've reached my current limit, I guess. That doesn't sound good. The power peaked out. Then it sounded like it stripped a gear, but then it ripped all of its fixings out of the board and the motor. So those fixings gave way, which was the weak spot before. That's pretty impressive still. Let's take a look at what the damage is. This rear mount is cracked, the middle mount is cracked, the front one's intact. Now this was in nylon, but fairly thin layers. I never replaced this one. I think there's only 2 perimeters. This was PLACF, I think a few more perimeters, but again, I don't think I replaced that. This is polycarbonate. This is Polymaker's PC Max, and it's actually ripped the screw out of the board, and that's still intact. I can't back drive the gearbox, so there's clearly some damage inside, so I'm going to have to take it apart to look at that. And none of these are bent, so that upgrade worked. I can see what looked like a load of teeth inside of here. Ooh. Yeah. Look at that. That metal gear has made mincemeat of the Planetary Gears. Which is surprising, because we actually went a lot higher in torque on the static test. But it's completely destroyed them. Well, I set out to decide if I could actually make a mini Mantis using 3D printed 2-stage planetary gearboxes. And I think I could. I mean, I know I've destroyed this, and I destroyed many of the 2nd stage sun gears, which was the weak point, but it did get to 125 Newton meters of torque or more, and that's probably enough. However, I was slightly lazy in the design in the fact that I simply copied the 1st stage to the 2nd stage, when really I should have increased the size of these gears because they're taking so much more torque, and particularly the sun gear. So if I made this gear have more teeth, so it has more diameter and is bigger, can take more torque, I'd obviously have to increase these ones. Yes, the size of the gearbox would get bigger, but it's probably something that would pay off, and then I think it would be possible to get more than 150 Newton meters of torque reliably out of the gearbox. Double that up with a belt drive, and then you've got enough torque to make a mini Mantis. But just because I can do it doesn't mean to say that I should do it. I think that's where the Jurassic Park scientists went wrong. So I can produce quite low-cost gearbox because I can print most of it on an FDM printer, except maybe one sun gear that might need professionally printing. However, the electronics and motor is going to be very expensive, and on a hexapod you need 18 of everything because there's 3 degrees of freedom on every leg. I always said that I'd never build another hexapod after I finished the Mantis because it pretty much broke me mind, body and soul. This one might be a lot easier, but it's still going to be very expensive, so the jury's still out on that. Let me know what you think in the comments section below. Maybe you have some suggestions. Don't forget that I now have subscription on this channel. You can find the links below, and I also have a new channel called Denton's Den. On Denton's Den, I get to interview some of the people that I've met from my 3-decade career in the film industry specialising in creature effects. It's not just creature effects people, but I have to admit the first few episodes are quite creature heavy. So if you like that kind of thing, head on over to my other channel. I'll leave a link in the description below. And don't forget to like, share and subscribe. Bye!